What is a wave? Wave is a two partial differential equation, two time derivative in time is equal to two time derivative in space, you know. So it's basically also related with this is the differential boundary condition. It's a one-dimensional case in 1D, you know. In 1D example is that if you have a string, like let's suppose you sort of do that, you have a guitar string, and you pull that guitar string. This is the let's say 0. This is the length of the guitar string is L, you know, 0 to L, and then you let it vibrate, you know. Then you leave this one, then it's gonna vibrate something like this, you know. After certain second, it will be here, then it will come here, and then it will be here, and it will be here, and it vibrate back and forth, and this will be the rest, you know. After some time, it will go to rest, and that guitar string, this phenomena is basically formulated by this equation, because we have rate of change in space and we have rate of change in time when you basically leave this string, and the mathematical formulation of this phenomenon is governed by wave equation. You need the initial profile, means how much you initially pull the string. You also need two initial condition because this is a second order in time. So two initial condition, and then you need a boundary condition also. Boundary is a fix, so 0 t is equal to 0 is equal to 0. There is no movement at the boundary, so that's everything is 0. Then we use the method number 1 in the last class meeting. We use the method of separation of variable, and we get the solution u x comma t. So the solution was, now I need to go back, what was the solution? I think this is the solution, so why not I just copy paste it. So that's is the solution, you know. So that is the separation of variable technique. So the solution in that situation is this. So your solution is I have to do it again. But paste. So that's the solution. We can now just look one more time how the solution look like. So the solution look like this. So we have basically sine. It's a periodic in space, and it is also some sort of periodic function in time as well. You know, you can see that if the string is keep vibrating, it's like it goes say back and forth in the same, you know, in certain times, and in also space. So it's also periodic in space. We will see that in when we use basically a different way of calculating the solution in the second method. And this is how you calculate the an. This is how you calculate bn. These are the coefficients. So basically, if any math problem is practical problem is, all you have to do is you have to calculate an and bn, which is the integration of the function by these sinusoidal function sine x. Today I'm gonna show you the second method, method number 2, which is easy than the separation of variable, but not a really rigorous method. In this, I'm gonna assume let my solution u x comma t can be written as a Fourier. So it has a Fourier representation, minus infinity to infinity, c n t. So I'm going to assume my function is a periodic in x. So I'm going to expand it using, we're going to fix the t for a fixed t. I'm basically, this is function of x only. So since this is a function of x, I can write down the Fourier series of that by this, because the length of is a 2 pi I n divided by L t on 0 to L. That's my Fourier representation of the function 0 to L. What will be C and T? It will be 1 over L 0 to L u x t e raised to power minus 2 pi I n divided by L t. That's my basically Fourier representation of my solution. I assume that I can write my solution as a Fourier. Now what I'm gonna do, I'm gonna take that solution and plug into my equation. What is my equation? UTT is equal to C square UXX. So plug this in. UTT, 2 derivative of time, is equal to C square UXX, 2 derivative in space. And we do the term-wise integration or differentiation. So if I plug that one here, it's going to be n vary from minus infinity to infinity. And I take 2 derivative of this function, I'm going to differentiate under the integral sign. If I do that, this is the, there is a one typo here. And this is the x, not t. This is the x, and that is also x. And this is a dx for a fixed t. So if I differentiate this into the integral sign, this is a function of x, which is going to be stay outside of the differentiation, because differentiation is only with respect to t. So the differentiation of this is going to be dn 2 derivative of this function with respect to t, and this function will stay as it is. This is equal to c square, and that will be summation n vary from minus infinity to infinity. So when n is equal to 0, that stuff is going to be 0. So n is equal to 0 is not included, because when n is equal to 0, when you differentiate, because if this is a 0, that's going to become 1. So you have only c0 t, and that if you differentiate with respect to x, that's going to 0. So there is no 0 term related to that. But when n is not 0, you see what is going to happen. It's gonna be this is going to be you take the 2 derivative of space, which means you taking the 2 derivative of this exponential, complex exponential. So this is going to be c and t as it is, and if you take 2 derivative, this function is going to be a 4 pi square. I square is a -1, n square L square e raised to power 2 pi I n L x. That is the derivative of that function. So n is equal to, here you see that here n is equal to 0 is not the case, but we have here. So this will give you this c0 double derivative with respect to time t is gonna be a 0, which is not important to us. But when n is not equal to 0, if you compare the coefficient, is gonna be a C n double t is equal to this one. It's gonna be a C square minus 4 pi square n square divided by L square C n t. If we compare the coefficient of or like terms, you know, of this and that. So this is in now OD. This is the ordinary differential equation, second order ordinary differential equation in CET. I will a bit more simplify that one. So this is a Cn double prime t. This is give you basically C0t is equal to AT plus some constant B. You know, if you solve that one, this two derivatives integration one time give you AT, and the integration second time you get something basically t square actually. Yeah, what will be, would you take one derivative you get a, and then you take the second derivative you get zeros? No, that's also correct actually. So it will be of this form, but here I will get this is equal to c minus 4 c square pi square n square divided by L square divided by C n t. And if I solve that one for each n, I'm gonna get C n t is gonna be a n, because for each n this is a second order OD in t, in C is gonna be e raised to power. So the auxiliary equation is going to be r square is equal to minus 4 c square pi square n square divided by L square. Therefore, the r is going to be a plus minus square root of this minus 4 c square pi square n square L square. This is equal to plus minus I 2 c pi n divided by L. So you get I, there's gonna be a 2 pi c n L x, and then the second root is b n e raised to power minus I 2 pi c n L x. Okay, so this is the Cn, but we need to calculate what is the An and Bn. We still don't know that what are the Ans and Bs are. But we have the initial conditions. You know, we will use that one. So this implies okay, that should be T, because this is in a T, you know, differential equation is in T. Now take T is equal to 0 first. Take T is equal to 0. If I put T is equal to 0, you're gonna get An plus Bn, An plus Bn is equal to, because if I plug T is equal to 0, this is a 1, that is a 1, is equal to Cn0. But what is a Cn0? This is a An plus Bn. Your Cn0 is this, you know, because Cn is 0 to L, 1 over L, 0 to L, 0 x 0 e raised to power, you know, e raised to power minus 2 pi. Yeah, this is your 0. If you plug 0 here, so this is gonna be 0, but rest of the sign is same. E raised to power 2 pi n I L x with the negative sign t x. Therefore, an plus bn is equal to 1 over L, 0 to L. This is a f of x. This is a f of x, e raised to power minus 2 pi n x divided by L dx. This implies an plus bn is equal to Fourier coefficient of f. That is the number one. Now, if you differentiate this with respect to which one? Yeah, if you differentiate this with respect to time, one time, and then do that. Now, what is a Cn prime of t? If I taking differentiate with respect to one time t, is gonna be a an time I time 2 whatever that the coefficient is 2 pi c n divided by L, e raised to power I 2 pi c n divided by L t. And similarly bn this time is going to be a minus I 2 pi c n divided by L and e raised to power minus 2 pi c n L t. Okay, there is I here. And now I plug t is equal to 0. So this implies it's going to give me an minus bn, because this is a common, 2 pi c n L, then there is a I here, and this is going to give you what is a c n prime at 0. It's basically this 1 over L, 0 to L, ut x comma 0, because here you see that if you take the derivative of this with respect to t, only derivative hit here, because there is no x on there is no t in this portion of the function under the integral sign. So, and then this is going to be e raised to power 2 pi I n over Lx dx. This function is a gx because this is another initial condition. So this is going to be 1 over L, 0 to L. This is a gx e raised to power minus 2 pi I n x over L dx. This is a g hat. So this implies an minus bn is equal to g hat n divided by 2 pi c n divided by L time I. This implies an minus bn is going to be L g hat n divided by I 2 pi c n. And now what is your b an plus bn? This is the f hat n. If I add them, I'm gonna get, by adding 2n, 2an is going to be f hat n plus L g hat n divided by I 2 pi c n. Okay, and therefore, what is your an? An is 1/2, and that become 4. Similarly, you can calculate bn. Bn is gonna be you have to subtract them basically. Fn at this minus that is gonna be L g hat n. Okay, this is the an bn when n is bigger than equal to 1. Sorry, when n is not equal to 0. When n is not equal to 0. Let's see what happens when n is equal to 0. So when n is equal to 0, your solution is Cnt is equal to just At plus B. That's your solution. And therefore, what is a Cn0 is just B. What is a B? B is basically C0. C0 is f hat of 0. You can calculate. So B is your f hat. And if you calculate the derivative Cnt, you get just A, and therefore Cn hat at 0 is equal to A. Therefore, your A is G hat 0, because that is a G hat at 0. Zero Fourier coefficient. So therefore, basically A is equal to G hat 0 and B is equal to f hat 0. This implies Cnt, Cn0 is basically f hat 0 plus G hat 0 time T. That is your C0T. So let's see what is the final solution. The solution is now this: uxt summation n vary from, okay, the first thing is 0 is gonna be outside, so it's gonna be f hat 0, G hat 0 time T, and then the rest of the solution is here. N vary from minus infinity to infinity when n is not equal to 0. So let's see, where is the CNT? So where is the CNT? CNT is this, where AN and BNs are given. So CNT is AN e raised to power 2 pi I N C L T plus BN e raised to power 2 pi I N C L T. And that whole thing is a multiply e raised to power 2 pi I n. One has a negative sign, C and T. One has a negative sign. B1 has a negative sign, so it's a negative sign. So it's going to be 2 pi n x. That's it. If I multiply, I'm just going to show you what is the solution look like. That's all we are interested in here, because this solution is but bit more uglier than the separation of variables. So it's going to be an e raised to power. So this and this, if I multiply this one, you're going to say 2 pi I n. I can pull out 2 pi I n over L. So it's 2 pi I n over L I can pull out. And this is going to be x plus ct. And if I do the same thing, I can pull out 2 pi I n over L is going to be x minus ct. So this is your solution where an and bn. So you know that where an is, and you know what is a bn is. This is just f hat n, and your bn is much more uglier than that. What was the bn? The an is not even an and bn are here. Just copy paste. Yeah, so where an and bn are these. Yeah, so this is your final solution, in which is a look in this form. That's your final solution. But this solution is basically look at this form. Here is one important thing you need to notice: this x plus ct and x minus ct. So these are the two things you will notice in the solutions: x plus ct and x minus ct. And that's your a and that's your bn, and that's the solution is the superpositions of these complex exponentials. Let me show you what is the importance of x plus ct and x minus ct, and how this is related to our real world problem even. So I'm gonna go and share what. How to share. You see that this is the wave equation. So these are the waves. If you see in the oceans, you see these waves goes and back, and this is also governed by these equations, which is a two derivative in time and two derivative in space. And you see that in the solution, you have x minus ct and x plus ct. What is the reason that if you throw something in the water, the first what happens is this is the initial profile, which is basically create when the energy enter into the water, so basically you get that profile. But as you let the time go, these profile break into two pieces, and these two waves travel in the opposite direction, and that's what the solution is tell us, that x minus ct. So this is the translation of the solutions in the direction to the left, and this is the translation of the solutions which is basically moving in the direction of the right. And c, this constant c, is the speed of that profiles. So c, which is a c square here, so that divide into c and c, the one profile travel in the same speed in the right direction, and the other profile travel in the same direction in the left direction. So you see that that was basically a real world phenomena which happens, and that also is basically related with our solutions when we calculate the analytical solutions. So these terms are appearing here as well. So from here, what I can, so you see that the solutions look x minus ct, x minus ct. So from here, I can do the third method to solve, and kind of basically get an idea of calculating the solutions with a one more different method, the method number 3 now, to solve the same equation. Again, this is solution and the previous solution, they are same, and you will show in your homework that you have two different solution, the two different way of calculating the solution of wave equation, but ultimately the both solution are the same thing in the calculation end. So method number 3 is called basically D-Ambert, whatever that is there. Ambert solution. Or formula, sometimes they say. So this is basically also related to much more looking at the solution of this form x and t. So we see that the solution gonna have one profile which is gonna travel in this direction, and another profile of the solution is going to travel in this direction. So we're gonna assume that the solutions might have looked like this. We don't know what f and g are, but we suspect that when we see the real world phenomena, the solution must have x minus c or x plus c term in it. So from here, we're going to begin basically our start problem for formulating the solution. And how we're going to do is this. We're going to again assume. So all the time we basically assume something, and then we construct on the base whatever the observation we have. We're going to assume, we're going to change the variable. So okay, so I'm looking for a solution u x t, so my solution is u x and t. This is my function. I'm going to change the variable. I'm going to say let my r is equal to x plus ct, and my s variable is equal to x minus ct. Why I got this change of variable? From this idea that the solution gonna look like x minus ct, x plus ct, and it's gonna travel in two different directions. So that's why I change my variable into this. And you will see this change of variables will magically do something to the equation, which is easily to solve. We will be easily solve that equation. So what will be x then? So basically, because I have x and t, so I'm making the base substitution in x and t. So if I add them, they're both of, therefore is going to be r plus s divided by 2. That will be my x, and t is basically y. T is when you subtract them, so it's going to be r minus s, and this is going to be divided by 2c. Yeah. So now my u is a function of r and s, where r and s are function of x and t. This is my chain. Okay. So what I need to do is now this, basically calculus 3. I need to calculate what is a u over u. So basically I need to calculate u t t and u x x. You know, I need to calculate these two things. What is a u t t and what is a u x x. So I will start with the u t, the partial derivative with respect to u of t. So now you know that in the calculus 3, the chain is, you want to calculate the derivative of ut. So u first go from r to go to from t. That's the first chain. Or you can go from u to s and s to t. So that is the second chain. So by chain rule, this will be partial derivative of u with respect to r, and then the derivative of r with respect to t, plus the partial derivative of u with respect to s, and the derivative of s with respect to t. That will be total or partial, let's say partial. So let's calculate that. The partial, I can just write the ur is easily. What is the derivative of r with respect to t? If I take the derivative of r with respect to t, I'm gonna get a c. And what is the derivative of, this is a us, I'm going to denote by us short notation. This is a us. What is the derivative of s with respect to t? So s with respect to t is a minus c. So this is a minus c. So if I pull out c, is basically ur minus us. Okay, that is the, let's do one more time again the same chain, u over ut square. You know, this time the same chain, the derivative of this u over ur, derivative of this minus c ur minus us, and then the derivative of r with respect to t. This is gonna be again d over ds, because this time just u replaced by this. And this is a USUT. And if you take the derivative with respect to r partially, this is going to be a CURR minus URS, you know, partial derivative of with respect to r and s of u. And this is going to be again derivative of r with respect to t is a c. And this is going to be a c time URS minus USS, and derivative of this with respect to is going to be a minus c. Therefore, this is going to be c square. Therefore, this is going to be a c square URR minus URS. Since everything is a continuous and perfect for us, like this is a negative sign here because this is a negative. Therefore, this is equal to u. So USR or URS is the same thing. If you take the derivative with r first or s later, or s first and r later, this is the same thing because the function is continuous and everything is fine. So this is going to be, this is a plus, so c square URR plus USS, this is going to be a minus 2 times URS. Is that correct? Yeah. Now I'm going to calculate UXX also now. What will be UXX? So U square, I can give you the, it's going to be a lot easier to calculate. So I'm going to give you the final result, but you can verify. It's going to be a URR plus 2 times URS plus 2 times USS. Because it's going to be again, so first you go from U to R and R to X, So this term U, R and R to X, the derivative of R with respect to X is just 1. So it's even easy, it's not, you're not going to get a C. So, but if you repeat all these calculations, you will get to that, Now plug that thing into this. Plug UTT is equal to C square UXX. What is a UTT? So it's a C square URR plus USS minus 2 times URS is equal to C square URR plus USS plus 2 URS. So you see that this will cancel out from both sides, and you get minus C's also cancel out because C is a constant. So it's going to be a minus 2 URS is equal to 2 URS. Therefore, this is equal to 4 times URS is equal to 0. That's excellent. So this implies this is a U function of R and S is equal to 0 of derivative, partial derivative with respect to R and with respect to X. When a function whose double partial derivative is 0, what type of that function will be? So you can assume that U, R and S will be a function of R plus G times function of S. This is the reason that their both partial derivatives are 0. If you take the first partial derivative of R, you see that this is going to be 0. If you take the derivative of R, this is the function, no matter what function is here, because if it does not involve any R, the derivative of this is with respect to R is going to be 0. And once you take the one derivative with respect to S, then this is going to be 0. No matter what type of function is this, but the product, the derivative of R and S with respect to 0 is if the function is look like that. This formulation of the function has. Because you can see calculate, if you calculate derivative with respect to R, U R, you're gonna get f derivative of f with respect to R, partial derivative with respect to R. This is going to be 0, but this is a function of R only. If you take the S, you're gonna get this. So it means that's your formulation of your function URS should be the function of R plus the function of S. So, but if you plug back X and T, the function, because R and S is a function of X and T, what is a R? R is a X plus CT. And what is S? S is a X minus CT. So your solution look like that. Yeah. That's one thing is, but how to calculate this profile F and G? That's some interesting things to do, because we need also how to calculate F and G too. Again, you're gonna use the initial conditions. So let's, if T is equal to 0, if T is equal to 0, you get Fx plus Gx is equal to Ux0. Therefore, this is a Fx plus Gx is equal to Fx. That's your initial condition. If you take the derivative of with respect to t, and then set is equal to 0, you know, let's see what then in that situation what you get. If you take ut derivative, the partial derivative of this function with respect to t is going to be a f prime x plus ct times the derivative of inside outside, which is a c, and this is going to be a g prime x minus c t, derivative of inside is a minus c. If you plug t is equal to 0, now you're going to get f prime is derivative with respect to t only, x plus ct, sorry, 0, we're plugging t is equal to 0, f prime of x and g minus g prime of x is equal to c also, you know, so I pull out the c is equal to ut x0, which is equal to g of x. Therefore, this is a f prime of x, g prime of x, that's the total derivative, divided by c. Therefore, fx minus gx is equal to integration from 0 to x, g of x divided by c dx. I can change the variable of this. I can say c d c, because you don't want to have the same limit and same the variable, so you just change the variable inside. Because this was what, you know, because this thing can be also written as d over d dx of f minus g, and then you integrate both sides. So instead of writing the constant, I integrated from 0 to x, because that's the fundamental theorem of calculus that tell us to do that. So now we have the equation fx plus gx is equal to what? Is equal to fx, and then fx minus gx is equal to integration 0 to x g c over c d c. You know, yeah, that's these two things we have. Okay, so let's see, if I add them, I'm gonna get fx, which is fx plus 0 to x g c divided by c d c, and if I subtract them, it's gonna 2 times, so I'm gonna divide by 2, 1/2, and if I subtract them, you're gonna get fx over 2. So this minus that, so this is minus 1/2. Okay, these are my profile, fx and gx. These are the shape of my profile. So therefore, what is the final solution? Final solution uxt was fx plus ct plus gx minus ct. That was my final solution, you know, here, you know, fx plus ct minus x minus ct. So, and then I plug my f. What is my f? F is fx, but where is x? I'm gonna replace x plus ct, because I'm calculating at x plus ct, divided by 2, then plus 0 to x plus ct, because I'm replacing x by x plus ct. So this is a z c divided by 2c. Move to, I don't know why I move inside, but, and what is the g? G is a f x minus ct, because you're plugging x minus ct, divide by 2, and this is a negative sign here. This is 0 to x minus ct g c divided by 2 c d c. I'm gonna just write in a bit more elegant form. This is a 1/2. I can say fx plus ct plus fx minus ct, and then this one you will see that I can write this integral. If I switch the integration limit of integration, I can say x minus ct. I can change this minus to plus sign to 0 to 0, and then this is a 1/2 2c g c d c plus this one is always 0 to x plus ct g c d c. So therefore the solution is this f x plus ct plus f x minus ct 1/2 2c, you know. So 1/2 2c. So you see this integration starting from here, ending here, this integration starting from ending here. So I can just combine them because the integral is the same. So therefore, thus this is your final solution. uxt is equal to 1/2, which is a very elegant, well written solution. This is called D. Albert solution. That's the solution. So let's do one example. You will see that how to use this solution. You know, it's a lot easier actually to use the solution. So let's suppose example. Let's suppose you have a utt is equal to 4 times uxx. Therefore, c is equal to 2. ux0 is equal to sine x. ut x0 is equal to, let's suppose, cosine x. You know, I think we did that problem. You will see that in that problem we don't have to do much work to complete that problem. And this one is basically whatever the interval is, 0 to 1, you know, so the boundary is basically 0. 0t is equal to 0 is equal to LT. Okay, so the solution is simply this, you know. So uxt is equal to 1/2 fx plus ct plus fx minus ct. This is the initial. So basically, initial profile break into two pieces. You know, so that's just telling that initial profile has two shape. It's gonna break into two pieces of height half the height. So you see that that was the initial profile. In the next moment, it divide into two, but the height is divided by half. You know, if the height of this is 1 unit, this is one half, and each gonna travel into two different directions. So each is traveling in two different directions. And plus 1/2 to c x minus ct x plus ct g of c d c. You know, so let's plug everything there. What is your function? What is a f? F is a sine. So it's gonna be just simply sine x plus, what is the c? C is a 2t, and this is a sine x minus 2t, and therefore 1 over 2c x minus 2t x plus 2t. This is a cosine c d c, and then you can just do the integration. Therefore 1/2 sine x plus 2t sine x minus 2t plus 1/2 c. This is going to be a sine c 0, so not 0 to x minus 2t x plus 2t. The integration of cosine is sine c, yeah. So therefore this is a 1/2 sine x plus 2t sine x minus 2t, and therefore plus 1/2 c. C actually 4, so therefore that's, so t is a 2, and therefore 2c is a 4. This is a 4. So this is a 4. And sine x plus 2t and minus sine x minus 2t. 1/2, 1/4. What is a 1/2 plus 1/4? 1/2, 3/4. And this is a 1/2 minus 1/4 is 1/4. Yeah. Isn't that interesting solution? You see that if the velocity is a different, one profile is going with a different height than the other one, you know. But it's should depend on, because we change the g profile. G does matter, you know. G, which is the velocity, initial velocity of the profile, how you basically break the profile, is also give you a different height. One is going, the one which is in the right direction is going just the bigger